It's a pleasure to be here. So as Massimo said, I will talk about my book, A History of a Tenth of a Second. And at first glance, it may seem that we can ignore this history. After all, most events that occur within this short period of time cannot be perceived. Most persons take more than a tenth of a second to react. A history of this moment features no exotic expeditions, few great men, no lone geniuses, and only small, very small explosions. But in looking carefully at this moment, it appears strangely constitutive of modernity. The tenth of a second was repeatedly referenced in debates about the nature of time, causality, free will, and the difference between humans and non-humans. So in its most basic formulation, my book asks who, when, and how were we able to peer into these short moments? Considerable attention has gone into studying the microscope, so why not devote a similar effort into studying short moments of time? The basic question is connected to two broader themes, and one of them I hope concerns historians of science, and the other one historians more generally. So first, how does this history inform or change our view of science? And second, what does it mean to tell the history of such a short period of time? This second question, I hope, is related to its opposite. What does it mean to tell the history of longer time periods? So one of the first realizations that I had when I started researching this topic was that I was immediately led to investigate a much longer time period. Part of the mystery of the tenth of a second had to be traced to ancient civilizations. The idea of dividing the day into 24 hours and the hour into 60 minutes and the minutes into 60 seconds, in fact, had to be traced back to the contributions of the Egyptians and the Babylonians. Clocks started acquiring minute hands around the year 1600s. Clocks with a hand for seconds appeared only later. And clocks that measured the tenth of a second started to be coveted by scientists around 1850. At that time, the famous French scientist François Aragon, who is known for introducing the daguerreotype to the general public, he claimed that they were no longer, quote, a vain luxury. So it appeared to me, as it had already to numerous scholars, that the history of civilization could be seen as a progressive development of ever more refined measurements, particularly. And this history should not be limited to the history of clocks, but should include additional technologies. Many scientists were concerned not just with measuring, but actually with visualizing what occurred within a tenth of a second, and even shorter moments of time. Some important milestones in this history are the first use of flash by the co-inventor of photography, Henry Fox Talbot. He photographed using electric sparks. And other important moments are Edward Muybridge's famous images of a galloping horse that you can see here. And in the 1930s, the stroboscopic images produced at MIT by Harold Edgerton captured images in 1/3000th of a second. Today, you can record millions of frames per second. So, but in contrast to most historians, I noticed a strange paradox. During this period of progress and evolution, scientists returned again and again to a value that seemed eerily connected to ourselves. And this is the tenth of a second. Let me give a few examples that appeared frequently in the literature that I studied. If you tie a glowing ember on one end of the string and twirl it rapidly, if the coal makes a complete circle in less than a tenth of a second, the circle will appear closed. If you reduce its speed, the circle will appear broken. You can try this experiment with a cinematographic projector. If successive frames pass in front of the viewer at speeds faster than a tenth of a second, you have an illusion of movement. You reduce the speed, the illusion of movement disappears. If you look closely at a rapidly moving target and try to time the precise moment when it crosses a specific point, if you compare this moment against somebody else's, you would notice that your reactions differ for about a tenth of a second. If you step on the brake of your car when an obstacle appears in front of you, the number is again about a tenth of a second. Try to read as many words as you can in 10 seconds, and you will notice that the number is about 100. one word every 10th of a second. If you time yourself when talking, you will see that the time needed to pronounce each syllabus will never be less than a 10th of a second. And if you analyze the electrical rhythm of the brain, at rest it will average 10 cycles per second. So while certain scientists continue to work hard to chop time into finer and finer slices, others turn to the second mystery, the strange permanence and importance of this value. So these two trends appeared side by side, capturing the attention of some of the most important scientists and philosophers of modern times. So philosophers have often remarked on a strange paradox in our concern with time. The German philosopher Jürgen Habermas, for example, he explained how, quote, the new value placed on the transitory, the elusive, and the ephemeral, the very celebration of dynamism, discloses a longing for an undefiled, immaculate, and stable present. Or Michel Foucault saw a similar tension in modernity, which he traced back to the poet Charles Baudelaire. While Baudelaire described modernity in a famous phrase as, quote, the ephemeral, the fleeting, the contingent, the philosopher reminded us how this period was also defined by a desire, quote, of recapturing something eternal. So the limits in perception, reaction, and even cognition brought with them a host of philosophical riddles, paradoxes, and questions. Were they due to limitations of the processing speed of the brain? And if so, could it be increased? Could it be measurable? Did they point to particular physiological qualities of the human body beyond the brain, such as the speed of nerve transmission or visual persistence? What evolutionary function did they serve? Were they related to fundamental aspects of the universe and the cosmos? How did they veil our access to reality? And how did they transform basic beliefs of causality, movement, and even history? Answers to these questions were frequently volunteered to scientists, yet others' answers had to do with understanding the 10th of a second in relation to the much longer period of time known as modernity. Let me move to my second slide. So a scientist introduced the language of modern communications theory, employing terms such as message and transmission. They increasingly referred to this value. The mid-19th century descriptions by Hermann Helmholtz are characteristic. Hermann Helmholtz wrote, he said, when the message has reached the brain, it takes about 1/10 of a second, even under conditions of most concentrated attention, before volitional transmission of the message to the motor nerves, enabling the muscles to execute a specific movement. But what interests me about this quotation is that whenever you start to see scientists talking about our access to the world in terms of stimuli and response, it's always accompanied by the strange significance to the 10th of a second. A century after Helmholtz's investigation, you still had Thomas Edison's chief laboratory engineer remarking how communications were still marred by this delay. He said, "We all live on a 10th of a second world." So why did the 10th of a second gain such an importance in modernity? Different people would give different answers. A psychologist would most likely respond because of reaction time. Hugo Munsterberg, who was the head of the first laboratory of experimental psychology at Harvard, he described the consequences of this value in these terms. He says, if a playing child suddenly runs across the track of an electric railway, a difference of a 10th of a second may decide his fate. If the speed of reaction could be increased, another researcher explained, we could find a way to preempt death itself. It's sort of as if death is coming at a certain speed and you could sort of, just... An astronomer would most likely answer differently, saying because of the personal equation. The intriguing term personal equation referred to a worrisome fact that different individuals differed in their timing of star transits used for determining time and longitude. And it actually took the shape of an equation. You can't see too much here, but these are personal equations from the Paris Observatory taken from 1843 to 1864. This was a routine measurement performed in observatories because different observers timed the precise moment at which a star crossed the reticule of their a telescope in slightly different ways. So they compared the two persons, and they gave them a number in units of a tenth of a second. A cinematographer, on the other hand, would explain its importance in terms of visual persistence. Philosophers, historians, and sociologists would give additional answers, some of which would be central to the explanations of how we gain knowledge of the external world. I'll give a little bit of more general background. The tenth of a second was a distinctly modern and post-Cartesian concept. When Descartes described the reaction of a person to a stimulus in his famous treatise of man, reaction and stimulus occurred at the same time. He said it's exactly as when you pull one end of the string and you cause a bell to ring at the other end. Trust in the instantaneity of nerve transmission started to be questioned by the middle of the 19th century. What preoccupied thinkers after 1850 was the existence of a lag time between stimulus and response. Scientists became increasingly uncomfortable with the mind-body dualisms that characterized Cartesian philosophy and started to focus instead on interfaces, such as nerves, between these two increasingly problematic terms. This change was also distinctly post-Kantian. A long-standing Enlightenment and Kantian tradition treated free action as unquantifiable. But from the 1850s onwards, scientists increasingly turned to tenth of a second measurements to explore the mechanisms of thought and even of the will. So Edward Titchener, founder of the first laboratory of psychology in the United States, could claim that reaction time measurements were, quote, a crucial experiment demonstrating that mental phenomena were measurable. This period was profoundly disquieting and challenging for scientists. Slight variations in individual assessments of this period posed profound problems for the exact sciences. But I argue that the relevant problem for science was no longer principally based on long-standing questions of objectivity and subjectivity. So instead of struggling with the classic question of how universal objective knowledge was different from subjective knowledge, scientists and philosophers confronted the problem of observations that varied amongst and within individuals. The problem was not solely about humans against nature. It was about humans against humans. It was not about what was true, but about who was right. Disquieting 19th century disputes about the tenth of a second differed in important ways from earlier scientific controversies. New philosophies started focusing on hybrid problems, and various thinkers started working with concepts that went beyond the traditional categories of man, thing, science, society, politics. They heralded a new period in which these categories were precisely the elements that were called into question. And I will give you three short examples from my research. The first example is from psychology. As I mentioned, psychologists typically see the discovery of a lag time in human reactions as central to the formation of their own discipline. Reaction time ostensibly led the science of psychology into firm experimental and quantitative instrumental ground. Psychologists' focus on reaction time reached its apogee with behaviorism. John Watson, one of the movement's founders, explained that the whole purpose of psychology was, and I quote, to predict, given the stimulus, what reaction will take place. And one of the most important defenders of reaction time experiments in France, and one of the earliest ones, was a scientist called Charles Richet, who earned the Nobel Prize for Medicine in 1913. He also was the author of one of the most important textbooks of physiology of that period. And under the entity of brain, he stressed the importance of a tenth of a second. He said, an elementary cerebral vibration has a certain duration, and this duration is approximately a tenth of a second. And I love this image. I know you can't see it too well, but I think of it in contrast to the image that I showed of Descartes, in which you have the body of this little boy reacting to the fire. And here we're completely, the body is completely gone. It's been completely abstracted. And this is an ear. And the person hears the stimulus, and it goes from the ear to the nerve, and it goes to a center where you have discernment, association, choice, and then eventually it goes back. This is a muscle, and it executes a movement. So this is a huge change, focusing on precisely the interior of this sort of Cartesian mind-body dualisms. My second example is from astronomy. As I mentioned, astronomers reference the 10th of the second in the discussions of the personal equation. This term was related, although distinct, from reaction time. Personal equation errors surfaced in the bread and butter work of most observatories, determinations of time and longitude, which preoccupied scientists, astronomers intensively after 1850. The work of the astronomers was related to the work of the psychologists. For example, Francis Galton, known as one of the founders of eugenics, he thought that the personal equation was the sought-after link between physical and mental qualities. He recommended, quote, that a comparison of the age, height, weight, color of hair and eyes, and even temperament should be made with the personal equation in the various astronomical observatories at home and abroad. And personal equation errors also haunted something that was called the most important astronomical event of the century, and this was the transit of Venus across the sun. This event was quite exceptional because it was rare. Transit of Venus occur twice approximately every 100 years. And the reason why they're so important is that it lets scientists have a value for the solar parallax. And I'm not going to explain what the solar parallax is. It's a little bit complicated. But the reason why they wanted to have a number for the solar parallax was that with it they could have all the other constants, the most important constants of celestial mechanics. They could basically have what they called the scale of the universe. But the challenge consisted in timing the precise moment when an apparent contact between Venus and the sun. But 10th of a second variations in how astronomers assessed this moment made it extraordinarily difficult for them to have a precise number for the solar parallax. And the attempt, this is one of the images from a machine, the attempts to eliminate the individual differences in observation led to the construction of some of the first pre-cinematographic instruments. This is a daguerreotype that comes from this photographic instrument that is aimed at a sideroscope that follows the astronomical phenomena up in the sky. And you can't really see here, but there's a tiny little dot and then a big quarter of a circle, and the quarter of a circle is the sun. The tiny dot is Venus. So scientists hoped that they would able to find the precise moment in which the Venus and the sun made an apparent contact, and that with that they would be able to determine the solar parallax and the scale of the solar system. And these differences, of course, plagued many other astronomical observations: eclipses, occultations, comets, planetary phenomena such as sunspots, solar prominences, and flares. In 1895, the Lumiere brothers presented their famous camera, and they traced the origin of the camera to Janssen's instrument. Years later, the cultural critic Walter Benjamin would describe the potential of cinema in terms of the 10th of a second. In his famous work, The Work of Art in the Age of Mechanical Reproduction, he argued that film had turned the 10th of a second into an explosive dynamite capable of bursting open the prison world of modernity. He said, "Our taverns and our metropolitan streets, our offices and furnished rooms, our railroad stations and our factories appeared to have locked us hopelessly. Then came the film and burst this prison world asunder by the dynamite of the 10th of a second, so that now in the midst of its far-flung ruins and debris, we calmly and adventurously go traveling." My third example is from physics and metrology. Physicists and metrologists approached the problem of a tenth of a second in yet a different way. The same variations noticed by physiologists, psychologists, and astronomers affected even simpler measurements, such as measurements of length. And new scientific practices and technologies were developed to combat the errors that they brought about. Scientists first noticed that in the process of measuring rulers, the size of rulers, different individuals assigned slightly different lengths to these standards. These errors appeared when leveling an instrument or when using a micrometer when bringing two marks in line with each other. They also surfaced when observers tried to find the exact center of circles and dots and the precise alignment between distinct objects. They appeared even in such apparently simple activities as measuring the diameter of the sun and the moon. So scientists first traced the spreading of the personal equation errors from astronomy to metrology to the work of the English astronomer Francis Baily in 1835. That year, Baily undertook a very detailed project to determine the length of different standards. And in the process, he noticed a problem when he tried to bisect the dots of a ruler with the cross wires of his instrument. At that time, many rulers were simply divided by dots at one end and a dot at the other. Baily argued that because these dots resembled stars, the measurements of length were affected by the astronomical problem. Baily's work was alarming since it showed that the problems noticed by astronomers when reacting to a transit star was also present in the most leisurely and careful observations that they could undertake, observations where time was typically not seen as a factor. And this is one of the dots from one of the standards that Baily tried to determine the length. And he recommended that instead of having a vertical micrometer and trying to bisect the dot, that you actually had a little cross and that you approach the micrometer to the edge of the dot, and that eliminated some of the errors. He recommended that he complained that the dots were sort of pear-shaped and recommended that scientists use the short, straight rulers, little lines that we use today to divide rulers. So something that interests me is how these very minor design changes were connected to these big philosophical questions. The problems brought about the tenth of a second motivated some of the most important changes in modern physics. Because of these problems, René Benoit, who was the director of the International Bureau of Weights and Measurements in France, who was charged in providing a fixed standard of measurement, was led to the alarming conclusion that all matter seemed endowed with movement and even life. He said, "We recognize that matter, even if it appears to us immobile and inert, is in reality the seat of an interior activity constantly in play, and one can reasonably say that it is endowed with some sort of life." And this is not in a philosophical text. This is in a technical manual on metrology. Speed of light experiments in physics gained importance because of the errors in astronomy, especially those that had come to light during the transit of Venus observations. Interferometry, which is now a technique considered to be at the pinnacle of precision science, was developed to evade errors of this magnitude. A new definition of the meter in terms of light waves gained currency because of errors that haunted previous determinations of the standard. Albert A. Michelson, who you might know as famous for the Michelson-Morley experiment that was so important for the theory of relativity and a Nobel Prize winner, he developed interferometric experiments that solved some of the measurement problems described by Benoit, who actually brought him to France in order to try to restore to matter that sort of inertness and solve these problems. In contrast to previous speed of light measurements, where observers had to note the precise moment of time when a spark of light shone through a rapidly spinning wheel, or had to measure the displacement of a white spot on a screen, Michelson's apparatus no longer required that an observer react, and thus it became seen as the most precise ever. So this is one of the images of the interferometer that Michael used. And the interesting thing is, for me, is how a person interfaces with the instrument. So there is no longer a question of a micrometer, of an alignment, of a level. There's not a question of reaction. The problem here is a very simple of calibration of black and white lines, and then counting the white and the number of lines. And the number of lines was in the thousands. And at first, different people, skipped a number or two, so they developed ways in order to have agreement, employing an amanuensis, counting out loud, counting two persons, and it was only when two persons agreed on the same number that they were like, okay, we got it right. So the way that I want, in my book to look at this experiment, which has been central to physics and this transformation, is obviously, yes, of course, an increase in precision, but more importantly, a complete change in how scientists interfaced with the world in which reacting a change. So I'm very, very interested in changing across modernity the different ways and places in which fingers, eyes end up together with screens and keys. So for numerous scientists and thinkers, the elimination of tenth of a second variations in measurements represented the ultimate achievement of modern science. Measuring, mastering, and disenchanting this value was, of course, an important victory. A new understanding of stimulations and reactions as stimulus, as signals transmitted from instruments to the body, through the body, and from there back to the instruments was defined by reference to this number. It was thus essential in negotiating the connection between hardware and wetware, based on new concepts of communication and reference. It was decisive in establishing clear-cut differences between body and spirit, humans and non-humans, as well as nature and society, differences which helped frame a number of discourses in the post-Enlightenment era. So with technology as a handmaiden, scientists solved most of these problems. Interferometers, as I mentioned, measured minute differences in length. Cinematography and high-speed photography were used to capture these fleeting moments, and numerous other scientists used direct reading scales and other automatic inscription devices. This is the change of the laboratory that we see to this day. The 19th century concern with these moments lost much of its vibrancy with the appearance of these new instruments. Thus, at the beginning of the 20th century, scientists could celebrate that the previous century obsession with what the Harvard psychologist Edward Boring had described as the sacred tenth of a second had finally passed. This new understanding of short moments of time was connected to the rise of physics and its establishment as the privileged science of precision in modernity. It was related to the concomitant decline of philosophy and its prestige vis-a-vis science. And in the book, I cover a debate between Albert Einstein and the French philosopher Henri Bergson that hinged on the interpretation of these short moments of time. I won't go into it right now, but I need to say that Einstein's way of thinking about them reflected how they were handled in the sciences of his era. When he thought about them, he saw no mystery. He considered basically two ways of understanding time and these differences. One was in terms of physics, as they were revealed by numerous laboratory instruments, and the second was psychologically, as they were imperfectly captured because of our sensorial limitations. For Henri Bergson, the famous French philosopher who debated with a physicist in person about these issues, physicists ignored evident complexities behind these short moments. Yes, instruments had demystified them to some degree. However, we still needed to think about how they achieved this. The cinematographic method captured much, but what was most important, argued the philosopher, continued to escape between the frames. So not all questions were solved. Was an experimental system composed of stimulus, experimental subject, and recording device even valid? While this system has become ingrained in various sciences, becoming a staple for cybernetics, and providing the basic categories of a semiotic theory of meaning in which cognition itself is understood in terms of signal, messages, central processing, and response, it was once profoundly contested. And I will show you here an image that was at the center of this controversy when some scientists argue that the experiment where you basically had a stimulus, a person, and a recording device was valid, and those who argued that it wasn't. And it's from a myograph, a rotating drum that rotates quite quickly, and the paper is smoked. You have a little needle. But the important point is, you can't really see it too well, but this moment right here is the moment in which the stimulus actually occurs, and these little lines are the moment in which the reaction takes place. And one scientist, Jules Etienne Marais, who developed the photographic revolver that also inspired the Lumiere brothers, he argued that this was a perfect working experiment, that it actually measured the reaction time. The physiologist against, he argued, Ernst Bloch, who nobody remembers right now, sort of lost the debate, the controversy. He argued that it actually was not a valid scientific experiment because of these variations. And in fact, you could have sort of the experimenter decide to stand up in the middle of the experiment. It introduced free will. It was not, he argued, an exact physiological experiment. But of course, there are many reasons why experimental subjects no longer stand up from their chair when they're confronted with somebody in a white lab coat. So the point I want to stress is that controversies pertaining to the 10th of a second did not completely vanish. They were not entirely forgotten, even after numerous solutions were implemented in astronomy, physics, metrology, and even after the invention of amazing new imaging techniques, and even after reaction time research became part of the experimental psychologists' daily work. When philosophies contesting logical positivism started to gain prominence after World War II, some of these relied on alternative interpretations of this short moment. So underneath the success story of measurement, these problems motivated scientists and philosophers to rethink the basic categories of observation, theory, and experiment. Something in this delay and something in the history of this problem still needed to be explained. So in addition to Einstein and Bergson, we have Ernst Mach, Pierre Duhem, Carl Pearson, William James, Karl Popper, Michael Polanyi, repeatedly invoking the personal equation as an important element of their philosophies. It is this example that led Duhem to the conclusion, quote, that a crucial experiment does not exist in science, and that subsequently inspired Willard Van Orman Quine in his famous Two Dogmas of Empiricism. I will only talk about two of the examples, and this is Karl Popper and Michael Polanyi, and I will make it very short. So in his famous book, The Logic of Scientific Discovery, Popper used the example of the personal equation to illustrate how scientific hypotheses could never be unambiguously proved. At best, they could be falsified. He turned to the personal equation to make what he called a particular obvious point about science, that its purported objectivity was really only a type of inner subjectivity. The personal equation was precisely the discovery illustrating the need to consider science as a shared practice. And he said he has this amazing example. He asked, could Robinson Crusoe, cast away in an island, ever obtain scientific knowledge? Popper answered no. Why not? What would happen if he discovered his personal equation? Could it be considered a scientific discovery? It could not be considered legitimately scientific until it became disseminated and accepted by the larger scientific community. It was an absurd example. How could Robinson Crusoe discover his personal equation? Therefore, science is a shared practice. To Polanyi, the personal equation brought an additional lesson, again in a very interesting and illustrative example. It proved the inescapable presence of personal judgment in science. And Polanyi's example actually prompted Alan Turing to recant some of his claims about the ability of computers to rival human intelligence. The debate between Polanyi and Turing again turned to short moments of time. To build his case against artificial intelligence, Polanyi knew he, quote, could substantiate his argument by quoting a great Princeton astronomer, astronomer on the extremely troublesome errors varying from observer to observer. But he chose instead what he called a more homely illustration. He discussed with Turing a photograph showing the final instance of a horse race. In the picture, one of the horse's head appeared to be, quote, a fraction of a second ahead of another's. But the verdict as to the winner could not be established because, quote, of the projection of a thick thread of saliva, which extended, quote, forward by 6 inches or so, well ahead of its rival. And I just love that this is saliva biological. Polanyi explained how the decision of the winner had to be referred to the stewards of the Jockey Club. This example, according to him, made evident personal and interpersonal aspects of science. This dimension of science could never be removed, not even with, quote, the advent of the photo finish camera or any other automatic recording mechanisms. So the lessons that Popper and Polanyi derived from the personal equation helped a generation of historians and philosophers rethink the process of knowledge production. Technical improvements, I agree, did not solve tenth of a second riddles on their own. Many other elements played essential roles. Some of these were institutional. You had to create laboratories of experimental psychology that measured and measured and measured reaction time. You had to create centers of calculation dedicated to precision metrology that sent fixed standards everywhere. These institutional changes were based on new divisions between disciplines, such as between the human and physical sciences, and within them between physics and astronomy. They were marked by a shift in the status of astronomy as compared to physics. Sciences seemingly remote from one another, like physics and physiology that were once entangled, became increasingly separated. Other elements depended on new relations between science and the larger cultural sphere. For example, the attempt to solve the tenth of a second errors was related to technologies like cinematography that eventually escaped from laboratories where they were being developed as an ostensibly neutral way to solve the discrepancies in scientific observations. More broadly, understandings of the tenth of a second were connected to major attempts to fix the boundary between subjectivity and objectivity. Subjective perceptions were marked by these tenth of a second limitations of the body, and objective ones were the ones that overcame those. There was a new theory of testimony. Carl Pearson, for example, found that the personal equation, how it related genetically to people. And after paying attention to these short moments of time, he confronted Hume's theory of testimony and argued that it had to be revised by introducing new correlation techniques. And even scientists investigated how the variations not only happen between individuals, but even how the actual interface, the actual key in which observers interfaced with the instruments affected the result. And I just love this image. An astronomer is trying to figure out which key is better in order to time the precise moment at which an event occurs. And you have a little book. We have forgotten these ones, the button or the telegraph key, which was the one that was most widely used. So if we look deeper into the history of a tenth of a second, we find there a context of discovery that opens up in even the most standard measurement techniques. This view leads us to propose alternative to epistemological approaches described so far: logical positivist, anti-logical positivist, or post-positivists, all of which, either by accepting it, rejecting it, or reassessing it, continue to be marked by the ghost of positivism. The view that scientific production arises from observation, theorization, and experimentation can only be maintained by ignoring essential aspects of the history of a tenth of a second. Scientists observed, they developed theory, and experimented. But first, I want to argue, they redraw metaphysical boundaries, redefining the very meaning of what is considered to be human, non-human, and beast. They shape the contours and alter hierarchies between the social, the political, the historical, and the natural. It is more urgent to work on how these divisions arise and to understand the repercussions than it is to study derivative scientific controversies and results. So instead of trying to continue to fit scientific practices into a semiotic theory of meaning, we can see how traditional concepts of reference were already inoperative in 19th century scientific practices and continue to be disputed in certain schools of 20th century philosophy. The standard model of understanding our involvement with the world in terms of stimulus, transmission, central processing, reaction, and response already depended on certain conceptions of this number. Let me show you an image here from Edward's scripture that talks about the importance of reaction time for the larger society. And you see some of the most important political figures of the time, Queen Victoria, Lenin, and this is called a reaction chain. So he argues that a reaction of a tenth of a second could have world historical consequences so the term reaction chain is actually first from reaction time, then from the history of the atomic bomb. The tenth of a second can help us rethink these categories in broader terms, such as in terms of the relation of movement, which is marked by difference, to form, marked by repetition, and in terms of a sensory motor organization of science. New arrangements between keys, bodies, wires, clocks, texts, images, and screens were set in place in attempts to understand this moment and solve its problems. These experiments involved new behaviors drawn from practices of spectatorship, new feelings, new distinctions within the body, such as between retina, nerves, brains, muscles, and fingers, new organization of these elements, and even new divisions between matter and life. So by narrowing even more on our subject of study to a category which is much more basic than experiment, which is what historians of science have typically focused on, we can further expand our understanding of measurement beyond its social context. So let me move to the conclusion. Let me conclude by returning to the question with which I opened my talk. What can we learn through a detailed history of such a short period of time? This moment, I argue, sheds light not only on the historical period in which it gained importance, which is you can trace quite precisely from the mid-19th century to the early 20th century, but it also helps us understand common historical conceptions. It offers us a way to rethink modernity both as a chronologically delimited period and as a conceptually defined category. Let me turn to the famous anthropologist Claude Lévi-Strauss, who explained how the scale of time chosen by historians actually reflected on their own cultural status. He said, civilized cultures organized history by using both, quote, ordinal numbers that denoted succession and cardinal numbers that expressed a distance between them. These numbers, he argued, fell into distinct classes. He said the date 1685 belongs to the class of which 1610, 1648, and 1715 are likewise members, but it means nothing in relation to the class composed of the dates 1st, 2nd, 3rd, 4th millennium. Nor does it mean anything in relation to the class of dates 23 January, 17 August, 30 September. Comparing history written at the scale of millennia against a completely different genre, which he called hourly history of each day, Lévi-Strauss argued that these two categories belong to, quote, different species. The smaller the time period between the dates, the more low power, that's his word, these narratives became, because they approached biographical genres and because they approached the myths of uncivilized cultures. While civilized cultures, he argued, turned to history, quote, people without history turned to myths. If finally numbers were rejected entirely and a synchronic view adopted, then myth replaced history. He argued there is no history without dates. So if we place an account of the tenth of a second within this progression, It appears even more low-powered than the biographical genres based on the day and very close to the myths of uncivilized cultures that reject numbers entirely. Yet there's also an aspect of the 10th of a second that can help us reevaluate the progression and problematize the progression described by Levi-Strauss and the categories employed by him. Consequently, we can rethink the great divide between the civilized and the savage, myth and history. Longue durée narratives are often based on common misunderstandings about the short periods of time that constitute them. If we look more deeply into the history of these moments, science no longer appears as a unique territory against which non-modern spaces can be compared. The debate surrounding the 10th of a second that I have briefly talked about reveal a space where the great dichotomies of modernity no longer hold. The spiritual is mixed in with the mechanical, the non-human with the human, the personal with the impersonal, the individual with the social, the natural with the political, and finally the primitive with the modern. So while mid-19th century problems of the order of the 10th of a second opened up dangerous floodgates between astronomy, physics, physiology, psychology, art, and philosophy, the gates were soon closed again. In the 20th century, standard systems of recording were set in place. The relation between analysis and synthesis was settled. Technologies once shared by media and science broke off to merge into one or the other, but not to both. A separation of the life sciences and the physical sciences strengthened. Physics emerged as the preeminent science of precision. Boundaries among scientists and between scientists and their instruments were reestablished. Deviations due to individual differences were minimized. A standard account of the expansion of quantification into the human sciences was canonized. These changes reflected a new configuration of science that characterized the 20th century, when a concern with 10th of a second individual variations was finally put to rest, but I argue that this happened only for a short moment of time. Thanks.